And last Thursday, we proved Green's theorem. And very briefly at the end, we talked about the, sorry, split screen up. Very briefly at the end, we talked about the application of how you can use Green's theorem to give you the area of a region of the plane. So we'll do an example of that now. I was thinking of starting the next chapter today, but I think it's a bit quick or a bit early. So there's just one or two other little applications of Green's theorem, maybe some examples which we'll work through this morning. So this is in section 1.20. So we talked to this last time. So remember, Green's theorem is this theorem here in the middle of the page, equation 202 there. And it relates the integral of a general, so there's no restriction on the P and Q, really, apart from the fact that they are defined and their partial derivatives are defined everywhere in the region R. So R is a simply connected region bounded by the simple closed curve C. P and Q are defined on C, defined on the inside, and they have partial derivatives everywhere in the region. In that case, the integral of p dx plus q dy over the closed curve C, reversed anti-clockwise, like I mentioned, that's equal to the double integral of the difference of partial derivatives, q dx minus q dy over the region R. Okay. Now, one example of this, if we choose very specific p and q's, and there are a number of ways of doing this, this is just one way. So we choose some quite simple p and q functions. So p of x and y is just minus y, q of x, y is simply x. Then what Green's theorem says is integrating that linear differential form around a boundary curve is equal to, I can put in the c underneath there, I guess with the c underneath, but it's understood that's what we're doing. Integrating around the boundary curve, you get twice the double integral over the region of dx dy. So on the right-hand side, the integrand is just the constant 1. Well, the double integral dx dy gives you the area of the region R. The area of the region. So you can rearrange this to get this nice expression for the area. The area is half of integrating x dy minus y dx around the boundary of a curve. Okay, I can show a little example like this in example 1.24. We'll do this on the overhead now. So this is section 1.20, example 1.24. Okay, so we're dealing here with an ellipse, which is a cosine t plus b sine of t. So this is the ellipse. Yeah, this kind of goes like this. It's kind of ellipse where you've got a on the x-axis and b on the y-axis. And this has the parametric equations x of t, which is a cosine t, and y of t, which is b sine of t. A and b are fixed constants. They determine the size of the ellipse in the two directions. And we want to get the area of the ellipse. So we can do this by performing this path integral. Okay, so we're going to integrate this linear differential form around the boundary E, and the convention is that we go anti-clockwise, and this will give us the area, okay, according to the previous thing. Now, in order to carry this out, I'm going to use the parameterization by t, so I'm going to convert it into an integral just of the single variable t. Now, t is the angle here, so t goes from 0 to 2 pi. To describe the ellipse. So this integral we can write as a half the integral from 0 to 2 pi. X is a cosine of t. Dy, well, y is b sine of t, so dy is going to be b cosine of t. This is dt. And then we subtract y, which is b sine of t. And that's multiplied by the differential dx. But if x is a cosine t, then dx is going to be minus a sine of t dt. So the dt is against everything. And this starts to look like something which will come out without too much bother. So we got a half of the integral from 0 to 2 pi, and this factorizes the AB can come out, and we've got cosine squared t plus sine squared t dt. And of course, this gives you a half the integral from 0 to 2 pi of AB dt, because cosine squared plus sine squared is equal to 1. And so integrating that would just simply give us a half 2 pi multiplied by AB, because the AB, of course, is a fixed constant. It doesn't depend on t. When we integrate t, it just gets multiplied by the length of the interval. The length of the interval here is 2 pi. So this comes out as just pi AB, okay, which is the formula for the area of the ellipse x squared over a squared plus y squared over b squared equals 1. And it looks correct. It does, of course, agree. NB disagrees with the known area for a circle. That's when A is equal to B. Say, that's funny. A is equal to B, which is equal to the radius of the circle. Okay, the ellipse is when it has, a non-circular ellipse is when it has. It's not a circle. It's kind of like a squash circle. There's different lengths in the two directions. But in the special case where both of them are the same, just equal to r, then of course you get pi r squared, which we know is the area of the circle. So it's a little example like that. I've got some more examples which we can look at in a moment. We're working on in the class. There's one last little application of it, of Green's theorem, which is to the notion of having path-dependent or path-independent integrals. When we first introduced path integrals along a curve, okay, which was quite a few weeks ago, we made the observation that you can have cases where you've got curves going from the same start point to the same end point. And if you do the integration along one curve, you can get an answer, and you do the integration along another curve, you get a different answer. That's not surprising. It's to be expected, really, because you're going through a different set of points. So your function, your linear differential form, p dx plus q dy, bound to behave differently as it goes through different points. However, there are special cases where you have a certain linear differential form, and integrating it between any two points, any two fixed points, it doesn't matter which path you go along. Whatever path you choose, you'll always get the same answer. And Green's theorem allows us to give a condition for when this happens. Okay, so this is in theorem 1.6. So you can have a look at that on page, whatever it is, page 36. Well, you see, Green's theorem says the integral along the closed curve of p dx plus q dy is equal to the double integral of the difference over the region. And the condition comes about, of course, by noting that if that difference is 0 everywhere, then the integral on the right-hand side is going to be 0. Okay. So this theorem 1.6 says that if you have a p and a q which have that special behavior, so that dp dy is equal to dq dx. So that means when you take their difference, it will be 0. Then the line integral, or the path integral from a to b, p dx plus q dy, it's independent of the particular path you choose between a and b. Okay. So we can give a bit of a sketch of the proof of that. So theorem 1.6. Well, we'll prove a simple case first. So here's one curve from A to B. Here's a curve C1. Here's another curve from A to B, C2. Now it's a little bit special case here. Assuming C1 and C2 do not intersect except at the endpoints. Okay, so the two curves C1 and C2, they avoid each other between A and B. Obviously, they have to both go from A to B because that's the setup. And so we want to show that the integral along C1 is equal to the integral along C2. Well, in order to do that, we consider the closed curve D, which you can take it either way, but let's say it's C1 minus C2. Now, what does it mean when you subtract curves from each other? Well, adding curves together is the operation of concatenating curves, which is taking one curve and putting it at the end of another one to make a longer curve. And the convention is that when you have a certain curve and you take minus it, that's the same curve but running in the opposite direction. So to just trace out D in red, and I'll just show it slightly off. So D is the curve which goes along C1 and then along minus C2. And I've just chosen the one that goes clockwise. It would have been slightly tidier if I had chosen the one that went anti-clockwise, but rather than scribble stuff out, I'll just deal with it. So I've chosen D to be the one that goes clockwise. So minus D, which is C2 minus C1. Let's see, if I was paying attention, I should have chosen D like this. This one is a curve going, it doesn't make any difference in the end, but it's a curve going anti-clockwise around a simply connected region R. Okay, these two curves between A and B that avoid each other, when you run the two of them together like this, along one and then back along the other one, you get a simple closed curve, which is going starting at A and ending at A. So we can apply Green's theorem to this. So Green's theorem will say that the integral along minus D of p dx plus q dy, this is equal to the double integral along R. I can never remember the order. dq dx minus dp dy. dq dx minus dp dy, dx dy. But by the assumptions in the question, these two partial derivatives are the same. So when you take their difference, it's 0. So that you're integrating 0 dx dy. And of course, that has to be 0. Okay, so you're just summing up the values of 0 across some region. So of course, you get 0. So this is by assumption in the theorem. Part of the conditions in the theorem. So that tells you that the integral along minus d is 0. But the integral along minus d of p dx plus q dy we can write as the integral along C2 minus the integral along C1, p dx plus q dy each time. So this implies that the integral along C2 p dx plus q dy is equal to the integral along C1 of QDX plus QDY. Okay, so when the P and Q have this special behavior, then it doesn't matter, and you want to integrate them from some start point to some end point, it doesn't matter along which curve you go. The answer is always going to be the same. And so that gives you some freedom. You can often, choose the most suitable curve, or choose a curve to suit your own purposes, which will enable the integration to be carried out in a nice, straightforward way. Now that's the special case where the two curves don't intersect. So what about if they do intersect? Well, I think you'll see how to do it once you draw the sketch of what's going on. So the general case would look something like this. You've got your A and your B. There's one curve going from A to B. There's a C1. And here's another one. There's a C2. It's a bit unclear what C1 is there. C1 is this one. C2 is this one. Okay, so these are two general curves going between A and B, so they do have a few intersections. But you can kind of see that it's just really 5 copies of the simple case. You can subdivide this whole thing so that it's just 5 instances of the simple case. Okay, so you split the curves up. Into, so we'll say C1 has got components C11, C12. How many does it need? 1, 2, 3, 4, 5. I think it's 5. Plus C13 plus C14 plus C15. C2 similarly, C21 plus C22 plus C23 plus C24 plus C25. So this is C11, C12, C13, C14, C15. You get the idea. Here's C21, C22, C23, C24, C25. So you split them up into these curves between the points of intersection. Then again consider D to be, well, this time I'll do it the right way around, C2 minus C1. Now, that won't be a simple closed curve, because it'll be a closed curve, but it'll have many self-intersections. Okay? So you're going out along C1 first and then back along C2. But you'll be able to split that up into the sum over J of C2J minus C1J, and J here is going from 1 to 5. But each of these, each C2J minus C1J is a simple closed curve. So covered by the general case. By the simple case we did just now. So when you, that means that integrating the linear differential form along C11 is going to agree with integrating it along C12, then apply it again to this pair. So integrating it along C12 will be the same as integrating it along C22, etc. So you're just applying it to each of the instances of the simple case that you can see in the general case. Is that okay? Any queries about that? It's a bit of a sketch proof. But it gets across the main idea. So just give you a chance to get that down. So there's loads of exercises here, and exercises 1.8 and 1.9. So you should be continuing to work on those for the tutorials and that. Do bring any questions you have about those to your tutor in the tutorials, me, Stephen, or Frank. And just for the rest of today's, we've got a bit of time left, about 20 minutes. I've just got some extra in-class exercises, which I'll put up on the board now in a moment, which I just prepared last night. And so we'll have a work through some of those. Any questions before we move on to that? Okay. So, yeah, here's a few of these class questions. So we can have a look at these. I've just got 3 of them here. We mightn't get to them all. So we can have a look at this first one. So in this first one, we're asked to, I'll just copy it down, we're asked to integrate this linear form. So the square root of 1 plus x cubed dx plus 2xy dy. We're asked to go along this triangle between the origin, 1, 0, and 1, sorry, that says 1 minus 3, but I meant 1 plus 3, actually. Sorry, there's a road minus sign. I'm going to change it slightly in the diagram. So I'm going to go to the point. Rather than 1 minus 3, I'm going to use 1 plus 3. So there's a bit of a misprint. Okay. So I've got the question here on the page. So we want to evaluate this. Where we're going along this, the region of the curve we're going along is this curve here. Okay, this is our C. Now, to do this directly looks very awkward because it would require some integration of that term, which is the square root of 1 plus x cubed. And that looks kind of awkward to do. So we should definitely, integrating that on its own, probably need to go via some trigonometric substitution or something. So perhaps using Green's theorem, this will be easier. Okay, it's not exactly a standard integral integrating the square root of 1 plus x cubed. So the 1 plus x cubed is your function p, and the 2xy is your function q. So Green's theorem says, let's call this integral I, that I is equal to the double integral over the region R, which is this triangular region, double integral over R of, I can't for the life of me remember the order it goes, dq dx minus dp dy. Now you can see how some simplification comes about because dq dx is, okay, 2y, but dp dy is 0 because there's no y in the function p. So when you differentiate it with respect to y, it just becomes 0. So the integrand simplifies, an awful lot. And so now we're just integrating over this triangular region R. So if I have it there like that, that y is the outer variable, then y is varying between 0 and 3. And for a given value of y, x varies. Well, x always goes up to x equals 1, and x begins on that line. And that is the line, this line here is the line y equals 3x. So, but now I want to express x in terms, you see, because the horizontal strips, the strips parallel to the x-axis, they all begin on that line. So they begin at a third of y. Okay, but of course, the inner integral with respect to x, 2y has no dependence on x. You can move that outside. 1/3 of y up to 1 dx dy. So this equal to the integral from 0 to 3 of 2y times 1 minus 1/3 of y dy. And so you can see it's just coming out to be a straightforward polynomial integral. Integral of a polynomial, so this is 2y minus 2/3 y squared dy, which seems to be y squared minus 2/9 of y cubed, evaluated at 0 and 3.
Is that 1/3 times by 1?
Yeah, sorry, 1/3, it's 1/3 of y. Sorry, it's not written in the best way there. Yeah, 1/3 of y, because it's the equation of this line, the hypotenuse there. X equals 1/3 of y. Okay, but shouldn't. Come on, you can do this. 9 minus 2/9 times 3 cubed. So 9 minus 6, 3. That's green. So, yeah. So that was far more straightforward than integrating actually around the boundary, would it be? Okay, because then you would have to be dealing with that square root of 1 plus x cubed term, trying to integrate that. You have to call on some non-trivial results for integration. And Green's theorem can also come in use even when, even when there's the curve in question, or the original integral in question, the original path integral, isn't necessarily an integral along a closed curve. Okay? There's nothing to stop you introducing, there's nothing to stop you closing the curve that you're given, and then making use of Green's theorem, and maybe making progress that way. Okay, so that's what the third example is like. So I'll show that on the screen now in a moment. I didn't leave it up enough for you before to get it down. Switch over now, but these scans of these pages will go up as always. So I think question 3 down there at the bottom, we can have a look at now. Considering this integral I given here, now it's the path we're asked to integrate along isn't a closed path. It's just the path which follows the curve y equals x squared from minus 1, 1 to 1, 1. It's this curve, this kind of U-shaped curve that comes down like this from minus 1, 1, follows y equals x squared down, it touches the origin and then comes up here. So it's not a closed curve. Now this function that you're asked to integrate isn't too, it's not really that difficult to integrate. You just turn it into a polynomial integral, but we'll avoid we'll avoid evaluating it directly, and instead show how you could use Green's theorem to help you to do it. By avoiding integrating along the path and instead integrating along a certain, integrating over a certain two-dimensional region. Okay, but you have to be a little bit creative, not too creative, but a little bit on the ball to see that you are free to add to the curve to make it a closed curve. And then recover the original integral later on. Okay. So this is the integral we're asked to do. Here's our curve that we're asked to integrate along. So from -1 to 1, and this is 1 up here, and we're asked to go this way. Now there's an obvious way to close this curve. Okay, it's an open curve at the moment, so you start here at -1, 1, you come all the way up to here. Well, if I just dash back along the straight line back to here, suddenly I've got a closed curve. Okay, so we can consider the related curve D, call this one D, which closes C by going in the straight line, and that straight line is got the equation y equals 1 from x equals 1 to x equals -1. So D is this whole curve. So Green's theorem implies that the integral along D of 1 plus xy squared dx minus x squared y dy, this is equal to the double integral over R over this region, which is enclosed here. So dq dx minus dp dy. dq dx, so differentiating q with respect to x gives me minus 2xy. And then minus dp dy. dp dy is again 2xy, so it's minus another 2xy. So this is the double integral over this region R of minus 4xy. Now what should I do? dx dy, 0. Okay, well let's make y the inner integral now and x the outer integral. I think that'll be more. Remember, you're free to make either, you're free to change the order of integration, okay, as long as you have the appropriate limits on the integrals. So looking at this from the outside, we want to integrate over R. So R is located between the x values of -1 and 1. Remember, when you're filling in these limits of integration, you always work from the outside in. Okay, so this is one integral inside the other one. So you look at the outer integral first. So we have to integrate from x equals -1 up to x equals 1. And then for a typical x value, we've got a vertical strip here. Now these vertical strips, these are running parallel to the y-axis, so we need to integrate across those. So you integrate. Well, yeah, you always integrate up to y equals 1, and the the point you're beginning on, the level of y you're beginning on, is given by x squared. Okay, it's a function of x, because the level you start at changes depending on the value of x. When x is close to 1, you start very close to 1 on the y value, and you end at 1, so it's a very short strip, because at the edges they're very short vertical strips, but near the middle, when x is close to 0, they're the longer vertical strips, because you're beginning at a much smaller number and integrating all the way up to 1. So this integral looks perfectly doable now. So we can quickly do it. Integral minus 1 to 1. Integrating minus 4xy dy will give us minus 2xy squared, evaluated at x squared and 1 dx. What's that going to give you? So putting in, so it's going to give you minus 2x minus 2x cubed. I've got all my minuses accounted for there. Like so. So this is integral minus 1 to 1. Just tidy up the minus signs. Well, it's 2 times the integral of x cubed minus x dx from minus 1 to 1. It's going to be 0, isn't it? X cubed minus x is an odd function. Yeah, so when you integrate it, you get x to the power 4 and an x squared. But when you evaluate them at 1 and minus 1, you get exactly the same value. So when you subtract them in the evaluation, it comes to 0. Okay, now this isn't saying that our original integral I is 0. It means when you integrate all the way along here, you get 0. So this implies, when you look back at what you've done, compare this closed curve we manufactured with the original curve C, which was just the U-shaped portion of it, we're going to get that our integral I is going to be equal to, well, it has to be equal to the negative of the integral along. So for D is made up of the actual curved portion C and the straight line portion D prime. Okay, so D prime is the curve which goes along y equals 1 from x from plus 1 to minus 1. So it's that straight line portion at the top. So this curve D is C plus D prime. So the fact that this integral by Green's theorem is equal to 0, this tells us that our integral, which is I, which is the integral along C of the linear differential form, this is equal to minus the integral along D prime of the linear differential form. Now, D prime is a straight line parallel to the x-axis, so that will simplify the linear differential form quite a bit. We're integrating with respect to x from 1 to minus 1. 1 to minus 1. Y is fixed at 1, so the dy part is equal to 0, and y is fixed at 1, so that means you're just integrating 1 plus x dx. So this is how the linear differential form, the original p dx plus q dy, that simplifies to this. And this, of course, is just, this minus sign I can use to flip the limits of integration. Instead, go along the other direction. Integral 2, isn't it? 2. I think it's 2. Doing it quickly in my head. Again, the x is an odd function, so that's going to contribute 0 because you're integrating from minus something to plus the same value. So you just get the contribution of 1. So it seems that original integral was 2. Let me check the answer here. 2. I'm right. Cool. So Green's theorem, that kind of implies or illustrates how Green's theorem can be like a tool that's floating around that you can often call upon to help you evaluate path integrals. Because even if the original path isn't a closed one, there's nothing to stop us closing it in some nice straightforward way, then getting the consequence from Green's theorem, and that will allow you to relate the integral along the original curve to perhaps your more straightforward or well-chosen closure of that original curve, in this context illustrated here. Okay? And it gives you the value 2, the original. Okay, so I hope you enjoyed those few examples. There's loads more there in the tutorial exercises for you to be working on. So do your best with those, and we'll see you in the tutorial. We'll see you all pretty soon anyway.